All right, A. Right, so for A, okay, our equation is work equals FD cosine theta. Right, so the force in A is 100, the displacement's 5. What is the direction, or the angle between the direction of the force and the displacement? No? 0, right? They're both in the same direction, going that way. So that's 500 joules. B, same equation. It's still 100 newtons, still 5 meters. But now the angle, right, the force is like that, and the direction's that way. So it's cosine 30. So you get 433 joules. Part C, FD cosine theta again. Now the block is being lifted up, right? So we have to apply a force up equal to its weight. Right? So the force up is 15 times 9.8. That's your force. It's going to be 5 meters. And now the force is up and the displacement's up, so let's come back to cosine 0. And so that's 735. Okay. Now question. This first example is moving at a constant speed. How is their work done if the speed's constant? Remember the guy with the oil can, or the fuel can on Friday, who said he was walking at a constant speed and there was no work being done. How can that be at a constant speed yet there is work done? Jeff?
Forces don't cancel out.
What forces?
There's only one force acting on that, and the guy had two, force of gravity and him holding it.
Remember the guy on Friday with the fuel can? Here was the free body diagram for that fuel can. Gravity and his hand, right? And they were walking at a constant speed, so his hand was applying a force, but it was 90 degrees to the displacement. There was no force keeping it going that way, so there was no work being done. Now that's not what we have here. What we have here is a block with a force of 100 newtons applied to the right. So if there's work being done, why is the speed constant? Jeff?
It's not perpendicular.
Well, that's why there's work done. But why is the speed constant? There has to be, right? Because the speed's constant. If this force is applied and there's nothing to slow it down, it's going to keep getting faster. Because it'll be accelerating.
There is something.
So there is something. So we're missing something. Friction, right? So what we're not showing is that while this force is doing 500 joules of work, what's doing negative 500 joules? Friction, right? There has to be another force, and that's doing negative 500 joules. The result of that is that there's no, what we call network. So the point I want you to know here is that forces do work. Right? There's two forces doing work here. One of them is doing positive work, one of them is doing negative work. Since both works are canceling out, you have no net work. There's that word net again. So you know how we have net force. Now we have the word net for work. So there's no network. When there's no net work done, okay, then the speed won't change because you don't have a net force on it. So what we could say here is that each force is doing work. There's no network on the block. I could also say there's no work on the block. And what I mean by that is there's no network on the block. Right? You should not be able to identify that the forces are actually doing work. We'll keep looking at this and we'll cement it in there. So friction's doing it, and this force is. Which one's doing positive work?
The application.
Right, this one, right? Because it's pushing in the direction of the motion. Which one's doing negative work? Obviously, friction, right? Their work is equal. The result of that is you have a constant speed. These two are not doing work. Why not?
Not moving up and down.
It's moving perpendicular to the force.
Right. There's 90 degrees between the direction of the motion and the direction of the force.
You're both right.
First, I think let's start off with a look at the free body diagram for the lifting phase. Gravity's pulling down, and therefore he has to push up. He has to push up with a force equal to the weight. It's moving at a constant speed. So the work is FD cosine theta. So it's 72.4 times 9.80. That's the force he applies. He's doing that through 0.65 meters. And the angle between the displacement, which is up, and the applied force is 0. And so we get 460 joules. That's what he's doing. To lower it, how does the free body diagram change? To lower it. The displacement's down. He's lowering at a constant speed. What do I change here? Sure? So to start going down, this arrow would be bigger, right? But as soon as it starts moving, they're equal again, right? Yeah. So we're just going to, this is going to be the lowering phase. It's this also, except for that. So now the work is still FD cosine theta. But now, what's the angle? Right, 180. So on the way down, he's actually doing negative work. Right, negative 460. Now gravity's also applied to the barbell, so it's also doing work. While he's doing positive work, what's gravity doing? Negative work. While he's doing negative work, gravity's doing positive work. Okay. The net work is 0, so the speed's not changing. So, if I do work on something, I change its kinetic energy. Now, what is kinetic energy? What is energy, to start? If something has energy, what can it do? If something has kinetic energy, it is moving. It can do work, right? How does it do work? How can something with kinetic energy do work?
Apply force over distance.
Right. It can bump into something and apply a force to that something over distance, right? So if something's moving, it has energy. It can do work because it's moving, by bumping into something. So that's the definition of energy, is the ability to do work. The equation for energy, for kinetic energy, 1/2 mvf squared. And it's the energy it has, the ability to do work that it has because it's moving. What's the unit on kinetic energy? Joule. Okay. How do I give something kinetic energy? What? Yeah, say it.
Do work.
Do what kind of work?
Strenuous.
Positive work, right? Positive work. If I do positive work, I make this higher than this. I give it kinetic energy. If I do negative work, I take this number's higher. I take energy away. So that's the whole thing. Do positive work, give energy. Do negative work, take away energy. This slide is showing me if I was a pitcher, right, and I was to throw this ball, right, let's say my fake catcher's over there, so I wind up, when I bring the ball right here, before I start bringing it forward, what's its kinetic energy? Right now, what's the kinetic energy? 0. How do I give it kinetic energy?
Apply force to it.
Another word. Give me another word. I do work on it. I do positive work. I apply a force through a distance, right? That's the key here, is that I do work. So now I'm doing work, and I let go. How much kinetic energy does it have? Kinetic energy equal to the work I did on it, right? Its initial kinetic energy was 0. I did positive work. That means that the final kinetic energy is going to be equal to the work I did. So now it travels across the room with the kinetic energy that I gave it, right? It's traveling towards the catcher. Here comes the kinetic energy towards the catcher. He wants to take the kinetic energy away. What does he need to do to it? Negative work, right? So now he applies a force that way, the displacement's that way, negative work. How much negative work does he do? Right, an amount equal to the amount of kinetic energy that was there. Takes it all away. Now the kinetic energy is gone. When V is 0, the ball is no longer moving. Kinetic energy is gone. Yeah.
So when you stop applying the force when you're throwing the ball, does that mean no work? Is work still being done?
Not by you. If there's no air resistance, then gravity's doing work on it, right, to pull it down. If there's air resistance, there's friction. There's negative work being done.
Okay.
Right?
Yeah.
So anytime there's a force, there's the potential for work to be done. And as long as there's a component of that force in the direction of the motion, there's work being done. So it hits my glove, and it stops. All the kinetic energy is gone. But the energy is not gone. Where's the energy now? We just talked about it. How?
Transferring heat between.
Right. That energy sped up the molecules. Now the ball's a little bit hotter, the glove's a little bit hotter. Thermal energy. Do you hear that? That's sound energy, right? When I do that, some of the energy of the ball moving has now reached your ears in terms of sound. Okay, so that energy goes everywhere, different forms. Okay, right now we're just looking at kinetic. Okay, I guess another thing to point out is that, this is important, in this equation, the FD is actually the network. So let me show you what I mean here. Let's say that I have a block, and I'm applying a force this way of 5 newtons. And at the same time, there's a friction force equal to 2 newtons. Friction. 2 newtons. Is the kinetic energy going to change? Let's say it goes 10 meters. Are we going to be changing the kinetic energy of that block over that 10 meters? Yes. Why?
There's an acceleration.
No, well, there is, but that's not how we want to phrase it anymore. No, forget the y direction. Why? There's negative work, but there's more positive work. If there's more positive than negative, that means the overall work is positive, right? That means the net work is positive. That means you're going to increase the kinetic energy. Now, if I want to calculate that, let's use our equation. Now, make sure you get this. Net work, just watch, don't write. Remember, I'm saying this is the net work. So how do I get net work? Well, I could do one of two things. Right? I could say the force, or sorry, what is the work done by the 5 Newton force? Answer? What's the work done by the 5 Newton force? 5 times 10, 50 joules, right? What is the work done by the 2 Newton force? Negative 20. What is the network? 30, right? So now I could say, well, then since the network, not network, the network is 30. That is equal to the change in kinetic energy. So now let me use this equation here. So network. So now I could do 30 joules equals this whole thing, whatever it is, right? The other thing I could do is make this the work done by the net force. So what is the net force? Here. What's the net force? 3. Right? So I could also think of it like this. So, or I could do 3 times 10 times the cosine of Force, net force is that way, displacement's that way. 0 equals that. Either way, I'm going to get the same answer, right? So when you do your work energy theorem, this needs to be the net work. So you either want to figure out the work of each force and get the net work, set it equal to this, or just do the work done by the net force. Okay? So whatever way you think is easier.